just in case you don't appreciate the difference between order n squared and order n cubed, you will learn to appreciate this difference in your code. Okay? It is huge difference. Okay? That is a marvelous reduction for you. Okay? In terms of computational power and speed. Yeah?
Can you explain again how if the Gaussian elimination part is order n squared and the substitution part is order n squared, that the...
No, Gaussian elimination is order n cubed.
Oh, okay. I just...
Yeah. Because you had to walk across rows, down columns, down the pivot.
Okay.
Yeah. And then this one here is order n squared. Okay. So order n squared, by the way, notice this was forward substitution because you started from the first one and go down. And then once you get this vector y, you can put it back into here, and now you have u and y. And then you can just back substitute for x now. So if you're just doing back substitution, same thing. It's order n squared, order n squared. 2 order n squared is just still order n squared. All you care about is, you don't care about the factors in front, you just care about how does everything scale with n. Okay? So 2 order n squared operations here. Okay, so let's write this down over here. So all right, so if you had this LNU matrix and you weren't using it, you'd get the right answer by doing the backslash, but you'd be dumb. I know I called you dumb. You're not supposed to do that in class. It hurts your feelings and makes you feel bad. But you do not pay order n cubed in a computation when you should be paying order n squared. Bottom line. We are now coding at a level where we're not just simply saying, do I get the right answer? It's like, do I get the right answer the fastest way possible? Okay? There's a whole different level of price now you're thinking about and in your computing. Yeah. Or does it? We will talk about the backslash in a minute. Right at the end, we're going to first go through how to do LU, and then I'm going to walk through exactly what LU does. I mean, the backslash does in its computation. Yeah.
I think that was my question, whether making these matrices L and U is also an n-squared operation. It seems like it has.
Yeah. So let's talk about that's next. So. Yeah, so you guys are jumping ahead. Ready? I know I don't want to tell you what's on the last page. You guys are the ones that probably are reading the last page of the notes already, just so you know the ending. By the way, it's a happy ending. Everything gets solved. But let's deal with that now, which is what I'm assuming here is that I have an L and a U. Okay? But really what I have is a matrix A. So where does this L and U come from? Okay? So let's talk about this step here. I still have to get the L and the U. And, unfortunately, this is order n cubed. But it's a one-time fee. Put this much down and you get order n squared afterwards. So it's one of those deals. You have to pay it once, but there is a big difference. So let me just say this. Gaussian elimination, every time you solve this, is order n cubed. Now think about what we're doing in our problem when we're solving this. You keep updating the solution. I got a new vorticity, resolve, new vorticity, resolve. You keep updating this to solve this. But this matrix is always the same. Every time you do this, you're putting in order n cubed. Now, if you were to use LU, you'd still have to find a way to decompose that matrix into LU once. But once you have it, every time you solve it afterwards, order n squared. Okay? Huge savings. All right, so one-time fee. This is your, let's call it your investment. So let's talk about how to get an LU matrix. So I'll come up with an example, show you how it works. You can LU in a lot of different ways, actually. So it's not a unique LU. It's basically, let me take a matrix A. Crap. Hold on. All right. So let me take a matrix A. Here it is. 4, 3, negative 1. All right, what I'm going to do is LU that. Now, the way to do an LU is you think about taking A and multiplying by 1. In particular, I will multiply by 1, the identity matrix. Now, the way this works is you've got to decide on an algorithm. And it has to go through all the way. When we do Gaussian elimination, sometimes we'll add them together, sometimes we'll subtract them, sometimes I'll add this to this, sometimes we'll subtract this from this. Sometimes I'll multiply this one by a factor of 2 and then add it. Sometimes I'll take that and divide by half and add it. In LU, whatever algorithm you pick has to be the same for all of it. You cannot change as you go along. In other words, if you decide, here's my pivot, it's going to be like Gaussian elimination, I'm going to pick that pivot. And what I got to do is decide on, right now, one algorithm to go through the whole thing with. Okay? And if I do that consistently through the whole thing, I will get my LU matrix out. Okay, so in particular, what I'm going to do is I'm going to try to make this number the same as this number, and then that number the same as that number. That's my algorithm. I have to pick something, but once you've picked it, you've got to go through the whole thing with that pick. So what I really want to do here, to make these the same, I have to multiply by negative a half. To make these the same, I would have to then multiply by a fourth. So somehow I'm going to first multiply by negative a half, take care of these two equations, then multiply by a fourth and take care of these two equations.
So you're finding L or B right now?
Both. Here's how it's going to happen. Since I'm going to try to get rid of this by multiplying by this factor negative half, the negative half goes here. This quarter is trying to get rid of this. That will go there. Okay? Now what's left over? Well, we still get the same equation. 4, 3, negative 1 at the top. Now what I've done is, multiply by negative a half. And, okay, now what I'm going to do, if I multiply this by negative a half, this row here, this row will give me negative 2. Right? And then it'll be negative 1.5, and then 1/2, right? And what I think I did, I think I took this and subtracted that from it. So I'll multiply this by the number, and I'll take this and subtract that row from it. So it's negative 2 minus a minus 2, 0. Minus 4 minus a minus 1/2, which is plus a half. Minus 4 plus a half is minus 2.5, right? 5 minus a half, 4.5. I have to use the same algorithm here. Okay, so if I multiply this equation by 1/4, I get 1 3/4, negative a fourth. And now I'm going to do this, subtract that from it. 1 minus 1, 0. 2 minus 3/4, 1 1/4. 6 minus a minus 1/4 plus a fourth, 6 1/4. Okay? I got some zeros here. This is going to be my U matrix, so all I got to do is try to make this 0. So I have to pick this as my pivot. Okay? So now I go down. It's just like Gaussian elimination. This is my pivot, and now I want to say, what do I try to do? I'm trying to make this number the same as this number. What do I have to multiply this by to make this the same number? Minus a half again. So what's going to happen, this minus 1/2 is going to be put in that slot right there. So this will keep going, and we'll have 1, 0, 0, negative 1/2, 1, 0, 1/4, and I'm multiplying by negative 1/2, so I put it right there, 0, times 4, 3, negative 1, 0, negative 2.5, 4.5, and when I do this out, I get 0, 0, 8.5. Okay, there it is. There's my L, and there's my U. Notice, because I could have picked to do this in many different ways, I would get non-unique L and U's. Whatever you pick as your algorithm, and notice my pick of an algorithm was to say, make these two exactly the same, and then take this, subtract from this. Take these, make the same, subtract from there. You could have instead say, pick a number that makes these two the opposite, add. Opposite and add, right? There's different ways to think about that. It would give you different LU reconstructions. Okay? But this matrix here is lower triangular, upper triangular. What was the cost of doing this?